Today we'll be talking about two open source frameworks that we've built and maintained. The first of which is called Ludwig. So the idea behind Ludwig is that it's an open source declarative machine learning framework. People don't really like writing deep learning code, and it's super error prone, and it can take weeks and weeks and weeks to get right. And we designed Ludwig to essentially describe your machine learning pipeline as a config file or a YAML file. And all it has is a few very simple components. You want to fine-tune Mistral 7 billion in the same way that we did LoRaWAN. You specify an adapter. So you can say, I want to use LoRa. You specify your base model. It can be any open source base model that you like. If you want to use quantization, which is a method to compress the model so that it fits on really cheap hardware, such as a T4 GPU, which is probably one of the lowest end GPUs that you can get. And then you can adjust trainer parameters. So all of a sudden, you can shift the way of thinking of training models from writing all of this PyTorch code to just thinking about an idea that you want to try, changing two parameters, and kicking off a job. And so once you have this YAML file, you just translate it into Python by importing Ludwig model, which is sort of our client, passing in the config, and then calling train. So extremely simple. And this is pretty much what we did for all of the LoRaWAN adapters. The one thing that's really cool about Ludwig is that we've run thousands of experiments fine-tuning models across various base models and data sets. And we've basically picked in we default to some of the best hyperparameters that generally maximize performance out of the box. So you get a lot of the learnings that we have just out of the box. Cool. So we're at half the battle. We can fine-tune models through Ludwig. There's also other frameworks I personally find, not just because I work on it, but this idea of declarative-based training is very powerful because you can very quickly iterate on your ideas and find an optimal model. So we fought half the battle. We have fine-tuned models. We know they're somewhat good from learning metrics and simple inference. But how do you go from there to actually taking it to production? And this is where most companies, most practitioners sort of fall short. The second open source project called LoRaX, which stands for LoRa Exchange. And the idea is that you can dynamically load in adapters, run inference in a very efficient way, and package all of this on one GPU. And you can serve, we've tested well upwards of 100 fine-tuned models on one GPU with virtually no latency degradation or throughput degradation. And I'll walk you through why this works and sort of what we've done. So the first idea is this notion of dynamic adapter loading. A lot of fluff words for a very simple idea that traditionally, when you have a deployment, you have a user, you have a request queue. And the idea is that you're a client, you send a request to your model, and it gets put in this queue. You generate a response, and you return it back. And you do this subsequently for many different requests. Right? That could come from many different users, something like that. But instead of doing this once per model, what if we were to create a request queue for each adapter and dynamically pop off those requests from the queue, load in that adapter, run inference, and then offload that adapter? So very simple idea. We're just making use of what LoRa does. It's very common, this idea of multi-tier weight caching. Again, fancy words, simple concept. The idea is just that the way memory is traditionally organized is that you have faster memory at the top, which can do computations really quick, but it can only hold very few things in memory. And then, as you work your way down to your solid-state drive or a disk, you can hold everything, but it's extremely slow to retrieve, to write, to read. And when a request, and these sort of like squares that you see, you can think of those as LoRa adapters. So when a request comes in, there's three things that can happen. The first is that your LoRa adapter is already loaded into GPU memory, in which case you just run inference, return the response. The simplest case. The second is that you get a request that comes in with an adapter, but that adapter is not already on GPU. So what you do is you always, as I just said, the memory is organized as a cache in this hierarchy. So you grab a LoRa adapter from the layer below. In this case, you'll go to CPU memory and see if the adapter is there. And if it's already loaded, you'll pull it into GPU memory and run that request. So again, it's pretty smart. It only does this when it has to. But the third scenario is, what if your GPU memory is full with adapters and there's a request that comes in for an adapter that's not already there? In which case, you need to do two things. You want to offload the least recently used LoRa adapter to a lower level of memory while prefetching or fetching the adapter that you actually need. And so that's how this mechanism works. It's all very dynamic. Sorry if I dive too into the weeds there, but it's super important to make this very efficient. With that, how do you actually use Lorax? There's 2 steps. The first is you spin up a Docker container with the model. And the second is that you can use either curl or a Python client. Just initialize the client and call generate. You can optionally pass in an adapter ID, which can be a local or on Hugging Face. And you can specify a response format. So if you want to do things like JSON mode, where you have fixed schemas and you have more reliable outputs, those are things that you can do as well. Other things that we support for those who are sort of deep in the weeds, we serve quantized models. There's a lot of quantization strategies. So we support most, if not all of them. We do CUDA graph compilation, which is another way to essentially speed up computations once the graph is compiled. Medusa heads is a new idea where you can decode multiple tokens at a time instead of a single token. So it speeds up inference. And then we're adding function calling support in the next 2 weeks. There's a lot of content I sort of went through. Sorry if it was a bit rushed. But there's this new Gen AI lifecycle that we can sort of summarize, right? You serve a base model through Lorax. We also support base model inference. You put that in production with your open source model. You collect data. Then you can use this data to fine-tune your model through Ludwig. And it's really easy to, as I mentioned, to iterate and try these experiments. Then you can choose to serve one or more of those, again, through Lorax. And you can actually do both base model and fine-tune inference through the same deployment. So super fast, super easy, and mostly low code, or at least we try to keep it as low code as possible. Don't want to plug this, but I have to. In case you just want to do it sort of in a managed way, and you don't want to plug it all in, there is this free trial that we have where it's built on top. Predibase is built on top of Ludwig and Lorax, and it's all managed for you. So I'll pause for 1 second in case you want to get that QR code. If not, totally fine. And yeah, I'll pause right there. Thanks so much.